if I were to take a string, make it taut, and if I were to pull back one part of it, you'd probably notice something like this. The thing is going to pop back into place, but you're also going to notice that the rope, string, whatever you have, will also still have a bit of vibration afterwards. And if you look carefully, you could even see the original displacement you have basically move down the line until the energy dissipates due to air resistance and such. So we might ask the question how we try to model this then with our given physics. So let's do that now. And first try setting up what that might look like. Give ourselves a little bit of space to do that. So it's like I have a straight rope, and then I have put some sort of a kink in it, like so. And once I let it go, the natural tendency is for this little bit of rope to pop back down. But it's not going to do just that. It's also going to want to travel along, since there's rope pulling it down over here this way, for example. There's some tension there, and if there's a force there, that's going to want to move that energy along then, actually. So you basically think that if you've pulled this back into place, you've put kinetic energy into the system, the same way by stretching a rubber band or a spring and putting kinetic or potential energy into that. So the energy has to be conserved, it needs to go someplace, and so you would actually can model this and say that this thing is now going to have some sort of forward velocity of a pulse. Now, putting tension in a string like that is not the only way to create a pulse. Another way of accomplishing So suppose again we have this sort of model of the pulse that we put into the string here. Is going to move forward with some velocity. We won't say necessarily what it ought to be, just it should be moving in some fashion. And we want to then describe this more carefully, so we should put coordinates on here. We should have something like the height that we have, something like the amplitude. So maybe we want to have amplitude and put that in terms of a y-coordinate. And we also want to describe how this moves along the string with the x-coordinate. So there will be some points along x where there's nothing, other points along the x where there's actually some amplitude there. And we're going to also expect this thing to move along. So it needs to also vary with time, so we really can't represent it too well just in this 2D graph. But it means whatever function that we want to have that describes, say, the amplitude of that wave, which should be described with not one, but two variables. The position along the string, and also at what time we have, because again, the wave is moving along, so this isn't just a static lump. We need to actually describe with time how that amplitude would change from point to point. So for example, if we say this is a snapshot, what we have here at, say, time equals 0, then we would say here at this x position there's some amplitude, but at a later time, maybe say 1 second from now, this might be flat and have 0 amplitude, and instead the pulse is down over here, again depending on what the speed is. So we need to have some sort of function that's describing this, and so that function should again be based on both the x-coordinate, the time coordinate, and also it should then also be based on the velocity of the pulse as well. So that's what we should have in our function. Let's also consider one other thing though. Instead of just a single pulse, what if I had a more continuous action going along? So for example, if I had my hand moving back and forth. Now if you looked at what my hand is doing like that, going left, right, stopping, returning, what should that remind you of if I was very careful with moving my hand? It speeds up, slows down, stops at the endpoints, returns to an equilibrium point. Basically, I can have my hand acting as a simple harmonic oscillator, and you've probably done this also then with ropes. or strings or anything like that, just start shaking one end of it and you can have pulses moving down there fairly continuously. So you're now taking simple harmonic motion and now turning it into a series of pulses, almost then a series of waves then. So let's now describe that with greater care. So instead of just one pulse, we're going to have multiple pulses. And so instead of just having one bump like that or so, it's going to be something a little bit more continuous. It's basically, well, if my hand is going back and forth and making oscillatory motion, what if I had my hand going back and forth, up and down, but also I was stretching this along the time axis? What would that look like? Well, in that case then, if I turn this into a coordinate system, and I made this a function of amplitude and time, basically just stretching out my up and down motion in one place, I would end up getting a sinusoidal function, just the sort of wave we would expect. So if we're going to have a wave like this, we're going to want to describe it more carefully. And the way we're going to do this is straight up, what sort of measurements of waves can we have? So we see a form like this, and one thing we can do is measure from one point on the wave to another point that repeats. So we see that these two spots on the wave are the same. It's the exact same point in the waveform, and because a wave is periodic, it should have this sort of repeated motion. So if I were to measure from here to here, this is then the amount of time it takes to get back to the same starting position it had. So this should be the period, capital T we use for period, of this wave. And we know there's a relationship between period and the frequency of a wave. Just a nice simple inverse relationship. So we could also do this if we want to look at not just the y and t coordinate. If we set up another coordinate system to describe the wave, if we look at the amplitude again, but also look at the position of the wave. So if we're looking at one snapshot in time rather than just one spot on the string, again, we should expect to see some sort of sine waveform popping out. And in this case, if we look from here to here, what that measures again is a period of getting from one point and then returning to it exactly. But in that case, this is a measurement not in time but in length. How far apart are the two repeating points there? And this we call the wavelength, and we represent that with the Greek letter lambda. Now, in both cases of what I did when I was measuring the period or wavelength, I was looking at the high points of the waves, which we would call the crest. I could have done the same thing if I looked at the low points, such as here, the troughs. I could have also done the points where we're going through the middle, but that might have been a bit more confusing because would I choose going from here to here or from here to here on the wave? You could see that if I was going from here to here, that's definitely a shorter distance than if I measured from this point to this point. Well, and if I draw the wave correctly, from here to here looks to be about the same wavelength as it is from crest to crest. So we see that if we look right here, where the wave is coming through, if we see it oscillating, it's going down through this equilibrium point. Here it's coming up. So these two are not the same. It's not exactly the same sort of thing. It's only at this point that we have the exact same form of the sine function, both here and here. So that's a bit of caution if you're going to try to measure the period or the wavelength using the waveform. So often it might be easier to use the crests or the troughs, but this is to your discretion, and it might be easier in some cases rather than others. Ultimately, though, the function that's supposed to describe this wave, and again it should be some sort of function of position and time, it's supposed to somehow produce the sine or cosine wave, and we'll choose sine somewhat arbitrarily. We know there should be something amplitude-like involved. How big do these waves get? We have the sine function, and that sine function should depend somehow on x, somehow on time. I'll leave that broadly here for now. So we might expect it, for example, to depend on the speed of the wave, and also then, of course, how it evolves then in position and time. So the book gives some derivation to try to get to this, but I'll just get to the final result for now. So the form we should have to describe what's going on is, again, the amplitude times sine function. And so there's going to be these factors of 2 pi in here, and the reason for that is because the sine function oscillates with radians, so it's 2 pi radians for a complete revolution or oscillation. So 2 pi is ultimately here as a conversion to go from units you measure in the real world to units you measure in the sine function system. If you're using the unit circle, that's why 2 pi is here. But we have that 2 pi multiplied there, and we have the x position and its relation with the wavelength minus t over the period. And if you're wondering, is there that minus sign? Again, because of the designs of the sine function, that this minus sign is ultimately actually representing the function moving forward or in the positive x direction. Might seem a little strange that the minus sign would do that, but in fact, that's how it actually ends up shifting the sine function as time goes along. Now, this is a somewhat ugly-looking equation, it would seem. We would like to clean it up a little bit, so we actually have some of these other variables that we put into place that are equivalent to other ones, and one of them we have is what we call the wave number. It's actually not an integer, it's not some nice whole number, but for whatever reason, I don't know the history of it, it's just called wave number. And it's a relationship then between the wavelength and then putting in that factor of 2 pi. So wave number is basically taking your wavelength but converting it in such a way so that you can put it into the sine function and have it translate out. And similarly, we have the angular frequency, which we have seen before with simple harmonic oscillators, and we know it has a nice simple relationship with the period, or if you prefer, similarly with the frequency, where again that factor of 2 pi is involved. So when we're translating from frequency, which we measure in units of the seconds that we're knowing of, or how long it takes to do a normal period in our measurements, to angular frequency, so that way it's the frequency as interpreted by the sine function. So if we just do those sorts of substitutions, what we're going to get is the same sort of thing we see up here, but a little bit cleaner. And so that's going to look like, again, the amplitude, sine function, kx minus omega t. Now, at this point, you might be wondering what happened to the velocity. Where does velocity come into play at all? Well, there's a nice relationship between the velocity of a wave and its wavelength and its period, or its frequency. As you can imagine, that if there's a certain period that it takes to go through a complete oscillation, and in that time it's going to move some distance, then that's going to tell you the velocity, because velocity is delta x over delta t. In that case, then, the delta x, the distance you go through when you're going through a complete period, is the wavelength. That's how the wavelength is defined. And similarly, the time it takes to go through one complete period is straight up the period. Or if you prefer, we could put this in terms of wavelength and frequency. And if we wanted to as well, we could put this in terms of angular frequency and wave number, all these being completely equivalent. So you see in this case, though, with the angular frequency and wave number are put right into our equation. So the velocity of that wave is actually right here in the equation. It's just kind of tucked away in a somewhat hidden fashion. But that all gets now described by the velocity of the wave. One point I should note, though, also this wave number k here, it has no direct relationship with the spring constant you had seen first with simple harmonic oscillators. So don't get those confused, and one thing in particular that points out why it's not the same is that wave number has units of inverse meters, or inverse length, while the spring constant had units of newtons per meter. So completely different units. Try not to get those two confused or think they might be equivalent in some way. Now, so far everything there just describes the wave mathematically, but we haven't gotten into any physics to say, well, how fast ought a wave go into there? Should it matter how big of a pulse I make? Should it matter somehow related to the string I use? Or are there other things to worry about? So again, if we were to think of our model of our pulse here, and we again think this pulse should be moving across with some velocity v, but we should also think then about what are the forces involved? What is actually pushing and pulling around here? So in a way, you would think that, well, there's actually a bit of tension going on everywhere. So this string should be held taut at first. If it were just laying on the ground, you really couldn't get much of a pulse through, you might notice. Only if it's taut are you going to actually get these pulses moving. So if we, say, look at a very small subsection, if we say, look just in this little box, this little region of the spring, or the string, I should say, there's going to be some tension force in this direction along the string, some tension force along this way, and since it's the same string throughout, it should be the same tension in both directions. But you'd see that this should have some sort of a net force downward. So we could talk then about that force. And of course also we do have some component things to worry about. So these tensions are not straight horizontal, straight vertical. There's some angular stuff involved. So really if we want to look at the force acting on some tiny little bit of string, it should be something along the lines of 2 times whatever the tension in the line is, sine theta. And if we're looking at a really small region, well, that angle is going to be quite small, so we could do small angle approximation. So we'll say it's 2 tension theta, where theta is measured in radians. Now, then also to describe how things get accelerated, well, that's going to also depend on the mass of that little tiny region we're looking at. So it has some amount of mass, and it should be related to then, well, how much mass do you have in any given amount of rope, and then looking over a tiny little subsection. So really we should be looking at maybe tiny little bits of mass, and that should be related to what we call the linear mass density. So mu has units of mass per unit length, and over whatever tiny little distance that we're looking at here. So really small infinitesimal region is what we should be looking at here. Now also notice that this pulse we have is somewhat rounded, so really we should be thinking of this in terms of centripetal force. What is causing this to kind of basically have, some sort of circular motion, it would seem, since we do have some sort of net force towards the center of some circle that we have here, or a very approximate circle. So we also remember that centripetal force is equal to mass times centripetal acceleration, mv squared over r. So we should include how big of a radius we have here at that point. Now, let's try relating these sorts of things all together. We know that the force here is supposed to be the only applied force that we described above. So that means we have 2 times tension theta equal to what little bit of mass we have. So that's mu delta x v squared over r. And that little region x, we should try relating it to the other variable we have here. So we could relate x, or delta x here, to the angular size that we have in this case. So delta x is going to subtend some tiny little angle relative to our point of rotation here. And how big of a region that subtends is going to depend on the length of r, the amplitude size here we have, and then how big of an angle we have. So really, delta x should be r theta. And theta here is very small, so it's basically an infinitesimal amount as well. And this angle should be subtending both to the right of that point and to the left here. So we can't just look at this part because otherwise it's not quite symmetric. So really there should also be a factor of 2 involved. So if we plug all of that in, we'll get mu 2 times r theta v squared over r. Let's move things out of the way. Give ourselves a bit of room here to do our last bit of algebra result. And ultimately we're going to relate then velocity to our variables that we can measure. And we find then that velocity is going to equal the square root of the tension divided by the linear mass density. So this means that if you have a really taut string, the wave speed velocity should be really fast, which kind of makes sense. If you have a lot of tension, it's going to want to force that string down really fast and move that wave along. And if you have a really massive rope, a really thick, heavy rope, that's really hard to accelerate, so it would be more resistant to these sorts of motions. So that at least makes intuitive sense to us, and if you look at the units, you'll see that you're going to get units of velocity. So that's just a nice little check. But now we have a way of relating the velocity of the wave to physical measurements, the force or the tension in the line, which we can measure, the linear mass density, which we can also measure, and now we can describe what would happen if we put pulses in here. But here's the interesting thing. Notice what doesn't come into play. The size of the pulse, that is like say radius r, the amplitude of the pulse we have, works itself out. So whether you put in a small pulse or a large pulse, the wave velocity should be the same.